Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good day to member of the floor. Today, I Muhammad Nazim bin Naha will present my research topic, study on heat transfer characteristic of airflow through tube bank difference between analytical and simulation approach for fuel-fired industrial heating process. The co-authors are also Ms. Mahani Muhammad Zamri and I019. Introduction. Heat transfer surface is a prominent in tube bank. We use in heat exchangers such as in power plant industry, air conditioning and refrigeration system, and transportation field. The reason of using this tube bank due to its better stability and efficiency as optimum arrangement influence the result. We found that the staggered tube bank is to be less favorable than the heat transfer performance of the inline tube array. The tube longitude and diameter characteristics as well as the transverse pitch were configured. The tube consists of geothermal water running through the preheating duct. Therefore, computational fluid dynamics, which is CFD, is used as it is a branch of fluid mechanics that has been increasing applied use numerical analysis and data structure to solve and analyze problems that involve fluid flow. Apart from that, CFD is also used as a tool which can predict fluid flow, heat and mass transfer, chemical reaction and other phenomena. Calculation across tube bank involve the Nusselt number and Reynolds number of heat transfer and flow parameter were met. The bank geometry and Reynolds number are the method applied to determine the turbulent intensity and generation. As a result, laminar fluid flow emerged due to the low Reynolds number obtained. Objective. The main objective of this project is to establish a computer code to predict the heat transfer characteristic of airflow through 4 columns of 4 parallel inline arranged tube bank for fuel-fired industrial heating process. Next slide is methodology. The CFD-NC simulation is performed using the industrial code fluid that use a digital method finite volume coupled to a multi-grid isolation scheme in CFD. Basically, the geometry and physical problem were generating construction drawing from fluid flow toolbar in Fluent Insys or Inventor or CATIA or computer aided design, which is SCAD. Hence, data can be processed then fluid volume is inserted. Discrete cell, which is the mesh, is to be filled with divide fluid volume could be transformed into structure or unstructured and uniform or non-uniform. The physical modeling and boundary is defined. The simulation begins and the equations are iteratively solved. Finally, the analysis and display of the resulting solution are performed using a post-processor. Boundary conditions are necessary for the CFD model to be implemented once the mesh has been constructed in order to solve the model and achieve convergence. Velocity and temperature are the boundary requirements needed for the intake flow, while the temperature of the air entering the duct and the temperature of the geothermal water exiting the tube are used for the outlet boundary condition. Each tube was given an inlet and outlet for the preheating duct tube bundle simulation. According to design data, it was expected that the flow in each tube was proportional to the overall flow. Table 1 and 2 show the boundary condition for the air side and temperature, and also table 3 show the inlet flow and parameter of preheating duct. Assumption and relevant parameter is what assume that under stable operating condition, the heat produced by the cylinder aluminum element was transmitted to the air pass. Result and discussion. Based on machine study, the quality of the mesh is crucial factor to take into account with respect to get correct result from a CFD simulation. The grid density, the discretization technique and converge error are just a few of the numerous factors that make up numerical error. Denser grid, higher are the discretization technique and the right time step can all reduce numerical accuracy. The varied length scale of the tube, where the tube length is 3.5 meter and tube diameter is 0.05 meter, might result is mesh with high cell density. The union between two zones is kind of the mesh is created through a non-independent interface. The figure shows the mesh of the heating duct, and this one shows the number of elements and nodes for this project. The velocity contours provide a broad overview, the flow behavior, and highlight its large-scale pattern. The recirculation zone between the tube and the recirculation region after the last tube are the only discernible large-scale feature in this investigation. From simulation, the figure shows distribution of velocity. For this one, the temperature distribution for tube wall show is obviously explained that the velocity temperature distributing and the amount of heat transfer are low. From simulation, we get the average of temperature on outlet, heat rejected by tube, and also heat transfer coefficient over the tube. We do analytical by following calculation to get the percentage of error, total surface heat flux, surface heat transfer coefficient, and also outlet the temperature. The entire temperature distribution in the flow can be seen by using temperature contours. Estimating the efficiency by heat transfer and the level of mixing in the flow can be done by looking at the temperature distribution and the formation of thermal boundary layer. This is final result: total surface heat flux, surface heat transfer coefficient, and outlet temperature. The tube wall's temperature is 383 Kelvin at Athens temperature of 293 Kelvin and a velocity of 4.5 meter per second, which may not be enough. The inlet velocity may need to be reduced. Lastly, conclusion. In order to compare the dimensionless value for all of the analyzed geometries, correlation were created. To examine the impact of the parameter on the mass of the preheat duct and the tube bank, a heat exchanger core was also dimensioned using the correlation created from the CFD. Finally, using the specified intake and velocity, the temperature distribution and cross-following heat transfer over the tube bank were complete. The result have been over the limitation of percentage error due to machine too detailed where the element was less than 500,000, which is could not perform convergence as per requirement. That's all my presentation. Thank you for your attention.